All right, everybody, let's get started. It is time for the show. Hi, everybody. Good afternoon, and welcome to the Lunchtime Discovery Series. It's good to be with you all for another edition of our program, gathered around the glow of the museum's YouTube channel for a chance to meet some interesting people who are doing really cool and interesting things out there in the world of science and nature, conservation, education, and more. We gather here most Wednesdays at noon to do just that. And the presentations are always great. I don't know how they do it, but the folks at the Office of Environmental Education seem to just hit it out of the park every single week, finding awesome people to come and share their knowledge and expertise and experiences with us. It's worth it to go ahead and, just like subscribe to the museum's YouTube channel, click the bell to get notified, because when we go live at noon every Wednesday, you're going to want to be here. You're going to want to participate. And what's great about this program is that being here on YouTube Live, you have the chance to interact as well. You can log into your YouTube account, and then you can post your knowledge, experiences, and questions for our guest speakers in the chat. I encourage everybody to jump in, at least drop like a little waving hand emoji and say hi to us, because we love to see who all is tuning in to our program. But more importantly, as we go through the program, as you have questions for the guest speakers, you can type those into the chat, queue them up for me. When we get to the end of the presentation segment, we do audience Q&A. I'll look to you all, the viewers, for your thoughts and questions to share with our guest speakers. So in that way, it's like we're all hanging out in the same room, meeting the guest speakers and having a great time. Now, for today's program, I'm excited to introduce today's guest. Really excited for this one because we have at Dr. Wendy Rocks on the program today. At least, okay, that's Dr. Wendy Bohon's Twitter and Instagram handles, where Dr. Bohon does just fantastic science communication work, kind of sort of generally around geology. Dr. Bohon is a geologist and science communicator, and we are very excited to learn about some of North Carolina and beyond's geology and earthquakes. And I don't know why we should all be afraid of rocks. No, I don't think that's what we're going to do. Wendy, welcome to the show.
Hi, Chris. Thanks so much for having me, and thanks for joining, everybody. I'm going to go ahead and do the thing where I share my screen and then make sure everybody can see it. How am I doing, Chris? Does it look okay?
Looks good to me.
Okay, so we're going to be talking about, and excuse me if I cough, I'm getting over bronchitis. It's been a long road. So we're going to be talking about earthquakes, mainly earthquakes on the East Coast, which is really interesting. But we're going to have to start this story at the beginning. So we're just going to start with a very cartoon simplified version of the Earth showing the composition. What's important to see here is that the crust is less than 1% of the Earth's mass. That's the solid outside part of the Earth that we live on. You can think about the structure of the Earth a lot like a hard-boiled egg. So you have the outer shell, which is hard, and it's also brittle. And so the brittle outside shell of the Earth, the crust, is broken up into these big pieces called the tectonic plates. These pieces are moving around very slowly over the surface of the Earth. One thing I want you to notice here is the outline of the continents, right? You can see those. And then you can see the whole plate is in a different color. So most plates are made up of both landmass and ocean bottom. So the outline of the land masses is not actually the outline of the tectonic plates. Another interesting thing to note is that the places where these tectonic plates come together are the places where we have the most earthquakes. So this is from the Pacific Tsunami Warning Center, and it's showing earthquakes around the world during 1 year. So there are literally hundreds of thousands of earthquakes occurring every year. And again, most of those are along the plate boundaries. And these plates can come together in different ways. They can slide past each other. This is called a transform boundary or strike slip boundary. This is what the San Andreas Fault is. It's a transform boundary, strike slip. They can pull apart from each other. This is what's happening in the mid-Atlantic ridge. So in the spreading centers in the middle of the ocean, we actually call this a constructive boundary because this is where new plate is being formed. Magma is coming up from the interior of the Earth, cooling, and then we're getting more plate being generated. In other areas, we have tectonic plates that are slamming together. And this is where one plate is diving down beneath another plate in something called a subduction zone. We call this a destructive boundary because as this subducting plate goes down into the mantle, eventually it will heat up and melt, rejoin, the constitution of the Earth, and eventually come back up and be part of a different plate. So that's a destructive boundary. One thing I want you to think about is the fact that the tectonic plate configuration that we see on this map is not the same tectonic plate configuration that we've had through geologic history. And I want to point that out by looking at one example right here. So you see this little blue plate called the Juan de Fuca plate, and there's this other little blue plate that's the same color called the Cocos plate. These were actually both once part of a larger plate called the Farallon plate. Well, where did that go? It subducted or took a dive down underneath North America. And so the only pieces that we can still see is that little piece in the north called the Juan de Fuca and the little piece in the south called the Cocos plate. How do we know that the Farallon plate used to be there? We can see it. So this is an image from something called seismic tomography. This is using seismic waves to look at the interior of the Earth. So when seismic waves encounter changes in temperature, changes in density, the boundaries between different things, they either speed up, they slow down, they can reflect or refract, and we can use those changes in the seismic waves to understand the composition and changes inside the Earth. So this little green area right here is actually the Farallon plate that has dove down underneath North America. So the plates are changing through time. And we know this. You've probably heard of some of those past supercontinents when all of the land masses were together. The most famous one was Pangaea. So this is a video showing you from about 20 million years ago to the present. And remember, we can see the land masses here, but the plates are much broader than this. In some places, the plates are being created, and in other places, the plates are being destroyed. This is the evolution of North America. So we're seeing the breakup here of Pangaea. This next bit is interesting because you can see India moving forward really quickly to slam into Eurasia, creating the mighty mountain range called the Himalayas. So here's an image showing Pangaea, which we just looked at, and that was around between 500 and 300 million years ago. And you can see kind of an artist rendition of the land masses that we know of now and where they were in that Pangaea configuration. And then here are some other supercontinents, Laurasia and Gondwana. One of the things I want you to look at, excuse me, is how North America and Africa slammed into each other. And this collision was very much like the collision we just saw between India and Eurasia that created the Himalayas. So when we had North America and Africa slamming into each other during Pangaea, it created a mighty mountain range like the Himalayas. Well, now we call that the Appalachian Mountains, the Adirondack Mountains, the Atlas Mountains, and the Scottish Highlands. Were all part of that long ago mountain range. As these continents are slamming together and then being torn apart, it's creating weaknesses in the crust. So mountains are made as we slam continents together or slam these tectonic plates together, and the mountains raise up along faults. And all of these different earthquakes are what cause these mountains to go up. And of course, as we're tearing these continents apart, that also is creating weaknesses in the crust, faults, and those faults are where earthquakes happen. So let's look really quickly at what an earthquake actually is. So we have a weakness in the crust, and that could be from some movement of tectonic plates, either a long time ago or in the present, and you have stress and strain that build up because of the plate tectonic motions. Eventually, you're going to exceed the strength of the rocks, causing them to break. And when they break, it sends out energy waves in all directions, and we feel that energy as shaking. So that's what an earthquake is. We know that we have earthquakes on the East Coast and in the Midwest. This is a map showing earthquakes above magnitude 4 in the eastern US since 1973. But if you remember back a few slides, I just told you that most earthquakes occur along the tectonic plate boundaries. But we are not on a tectonic plate boundary. We're actually in the middle of the plate. The tectonic plate boundary for North America is along the West Coast. The other plate boundary is in the middle of the Atlantic Ocean along the Mid-Atlantic Ridge. So why? Why do we have earthquakes in these places? Well, even though we're in the middle of the plate, that doesn't mean that there's not stress and strain building up within this massive tectonic plate. So this is some new research that's come out showing variations in the crustal stress field throughout North America. And this image can be a little bit confusing. The colors don't relate to the magnitude or the amount of strain. They're actually showing the type of stress and strain. So in this image, the red is showing compressive stress, where things are being squeezed together. The yellow is showing areas that are under shear stress, or things that are wanting to push sideways past each other. And then the blue areas are areas that are under tensional stress. They're undergoing extension. The little lines are showing the magnitude and direction of those different strain fields. So there are differences in different places, and stress and strain is building up inside North America, but very, very slowly. So I don't know if you guys remember this game. It's called Booby Trap. If you haven't played it, I haven't played it since I was like 5. And the idea is you put these they're almost like buttons, put these little buttons in, and then you turn a crank. And so you're basically putting all these little buttons under compressive stress. And as it squeezes them tighter and tighter together, eventually one of them is going to just pop out, right? It's booby trap. Bam. That's kind of like East Coast earthquakes. We're under compressive stress, and there's all of these old faults, all of these old weaknesses in the crust from those past collisions and tearing aparts of these different supercontinents. Those are still there. And so even though the stress is building up slowly, it's still building up. And eventually they pop off. So, excuse me, we know that earthquakes occur along faults, and we know there's lots of faults on the East Coast. But if we look at, say, the USGS Quaternary Fault and Fold map, we don't see a lot of faults here. They're all concentrated on the West Coast and kind of the American West, right? There's a little bit in South Carolina. You can see a little bit in New Madrid. Why is that? This is only showing faults that reach the surface. So not all faults reach the surface of the Earth. A fault is a three-dimensional structure inside of the Earth. A fault line is where the fault intersects the surface of the Earth. If it doesn't intersect the surface of the Earth, it's really difficult to put on a map. Most of the faults that are in the East Coast and the Midwest are ancient, millions and millions and millions of years old. And they may not have had an earthquake in 1 million years, 2 million years, 10 million years. And what else has been happening? We have the Appalachian Mountains, right? They were once the size of the Himalayas. And this whole time, they've been shedding sediment. They've been eroding for millions of years. And so they're covering up all of these old faults with lots of sand and silt and soil. So we don't see these faults at the surface. Now, people have done geophysical investigations to figure out where these faults are buried in the bedrock. So for instance, this is a fault map from South Carolina, the South Carolina Emergency Management Division. If you don't follow them on Twitter, you absolutely should. They're fantastic. And then this is a map of part of Virginia, showing some of the faults that are located there. So there are some fault maps of the areas, but again, because most of those faults don't intersect the surface of the Earth, they're very difficult to map. So what we do instead is we look at areas where we know there is seismicity or where earthquakes occur. So this is a map from the Geological Survey of Alabama showing these different seismic zones that we know about on the East Coast and in the Midwest. We have the famous New Madrid seismic zone over here in the Mississippi River Valley. There's the Southern Appalachian seismic zone, which is often called the Eastern Tennessee seismic zone. There's the South Carolina seismic zone, and they don't have it labeled here, but up here is the Virginia seismic zone. So we're going to go through some of these different seismic zones and the earthquakes, famous earthquakes that have occurred in these locations. But one of the things I want to point out, you look at this map and then look at the USGS seismic hazard map, you can see that these different zones are outlined as having higher seismic hazard than the areas nearby. So first, we are going to look at South Carolina. So in 1886, at about 9:50 at night, it was a heat wave. And so a lot of people had stayed home during the day and were out and about at this time of night at 9:50 when the earthquake occurred. It was around a magnitude 7.3. It's really difficult with historical earthquakes to pinpoint an exact magnitude because we have to rely on the records of the people that are telling us about what happened as well as pictures of the damage to give us a good assessment of what happened. So there was quite a bit of damage around South Carolina. At the time, it was around $5 to $6 million worth of damage, which was quite a bit. It derailed trains, knocked down buildings, and there was quite a bit of liquefaction. Liquefaction happens when you have soft sands and soils and a high water table, like you often do in the coastal plains and the East Coast. And what happens is, as the seismic waves pass through, they force the water up towards the surface. This causes all the little sand grains to separate and often almost turns the ground to quicksand. It can also liquefy sand lenses that are underneath the surface and cause them to shoot out, almost like eruptions of sand. So that's what you see in the upper corner there is some liquefaction features from the Charleston earthquake. And South Carolina still has earthquakes. There's a couple earthquakes there felt every single year. And the last few years have been very active because they've been having a little seismic swarm. There have been more than 40 earthquakes in Kershaw County. The biggest one was a magnitude 3.6. The smaller ones are magnitude, ones and twos. They're really little, but people were concerned. Seismic swarms are not super common in South Carolina or on the East Coast, but they happen fairly regularly. There was one in Alabama in the 2000s. They happen very often on the West Coast, but just a good reminder that, these places, this is earthquake country. Everyone can feel shaking from an earthquake. So now we're going to go back to sort of geology 101. We've talked about how continents are colliding together and how they're, ripping apart, but how? How do they rip apart? Basically, you end up with a mantle plume or an area of really, really hot rock that's coming up from deep inside the earth. And that causes the ground above the plume to dome or to lift up. Eventually, it's going to split. And nature is so elegant, whether you're looking at a mud crack or if you're looking at one of these large scale features, they tend to break and crack in the same way. So when you have these domes, they crack into 3 arms. This is called an allocogen. And 2 of these arms will actually start to spread and open up. One of them will not, and that's called a failed rift of the allocogen, the failed third arm. This actual process is happening right now in Africa and the Middle East. So you have an allocogen right here, this triple junction. The Red Sea and the Gulf of Aden are 2 of those arms that are opening up to create an ocean. And then you have the East African Rift Valley, which is the failed rift, the failed third arm of that allocogen. There's lots of earthquakes here, lots of volcanic activity here, but this one will not continue to open up while this one will continue. Where's another place that this has happened in the past? The mid-continent of the United States. Let's focus on the Reelfoot Rift, which is one of these failed third arms of an allocogen. This is more commonly called the New Madrid seismic zone. That's the one right over here. All right. And again, in the New Madrid seismic zone, the faults that have had earthquakes don't make it all the way to the surface. We can't see the surface expression or the fault lines. And so what we can see instead is the seismicity associated with those fault lines, but at depth. So earthquakes happen deep below the surface of the earth, not generally near the surface. So even if they're shallow, that means that they're 2, 3, 4 miles below the surface. So this map is showing earthquakes with magnitudes equal to or larger than 2.5. And you can see that they form these linear trends outlining the faults of the Reelfoot Rift or the New Madrid seismic zone. In 1811 and 1812, there was a sequence of earthquakes that occurred here that lasted for several months, including 3 quakes of magnitude somewhere between 7 and 8. We used to think it was closer to 8. Now, work by Suhoff and others has placed those closer to the early 7s, but they were felt significantly across the East. So this is a modified map showing the shaking of intensities of shaking across the East Coast and Midwest from these earthquakes. So they destroyed settlements along the Mississippi River. They caused some minor structural damage as far away as Ohio and Missouri, and they were felt from Connecticut to South Carolina to Louisiana. They caused some really interesting things to happen around the Mississippi River. So the banks of the Mississippi collapsed in some places. There were landslides in Kentucky and Tennessee, and elevation changes along the Mississippi River floodplain, including in one place where the land was lifted up such that it dammed up the Mississippi River, which caused it to flow backwards for a short period of time till it overtopped the banks and then continued on its way. These earthquakes, very much like the earthquakes in South Carolina, cause significant liquefaction over really great distances, as well as ground fissuring and then the venting of water and sediment, again, like those almost like little tiny sand volcanoes. Paleoseismology, or the study of ancient earthquakes, along with archaeological findings in the area, show that there have been sequences of earthquakes like this in the past. And based on what we know right now, it seems that they occur about every 500 years. Now, this is called the recurrence interval of an earthquake, or how often an earthquake will happen. And I want to point out that earthquakes aren't like babies or the phone bill. It's not like, we say, okay, every 500 years, and if it doesn't occur 500 years, you're late. No, it's more like the conditions become right again. The fault is ready to have an earthquake, but we don't know exactly when it's going to happen. It could be 100 years before that or 200 years after that. The Earth is a huge natural system with a lot of variability. So when we say they occur about every 500 years, that's when we think of the fault as being ready to produce another earthquake, not necessarily when that earthquake will occur. All right, let's get back to our tour of seismicity. So now we're going to head, where are we heading? We're heading to you in North Carolina. You guys probably have all heard of this earthquake, the magnitude 5.1 Sparta quake on August 9th, 2020. So that quake occurred right over here, and this is in the very edge of the Southern Appalachian seismic zone. There have been other earthquakes of around this magnitude that have occurred in this general area. So in 1916, there was a magnitude 5.2. Close by in 1861, there was about a magnitude 5. Just to the north, there was a magnitude 5.6 in the late 1800s. And then we're going to talk about this earthquake that occurred in Virginia next. The map down here is showing the distribution of people that felt shaking from this earthquake. So each one of these little dots is a person or several people in a particular area, and they're telling us something about the amount of shaking that they felt. Now, this earthquake was really interesting because it was the first documented surface rupture in the eastern United States. So this was the first time that we've ever seen one of these East Coast earthquakes actually intersect with the surface of the Earth. Now, this is really helpful for getting us to understand the fault. Here's a picture from a poster at the Southern California Earthquake Center meeting from Hill et al. That's showing the fault reaching the surface. So you imagine that this red line was connected to this one down here. This is the fault that moved it. So remember that map showing the different stresses across North America? This area is under compressive stress. It's being squeezed. So this is a thrust fault. And they named this fault the Little River Fault. So now we're going to go up to that earthquake here in the central Virginia area. That was the magnitude 5.8 Mineral Virginia earthquake. What I'm going to show you now is a really interesting animation, but first I have to explain what was happening geophysically at the time. There was this huge, and I was working in Arizona on this project when this earthquake happened. There was this huge project called the Transportable Array. And this was an array of 400 seismometers that were being moved across the United States very slowly. So they would put the seismometer in the ground, it would stay there for about 2 years, and then it would leapfrog forward to the front of the line. And what that did was create this moving array of seismometers that acted almost like an ultrasound wand. So we could see what was underneath the surface of the Earth with much greater clarity. So each one of the dots that you see here is a seismometer. You can think about it almost like a pixel in a camera. The more pixels you have, the higher resolution you have. The more seismometers we have, the more detail we can see deep inside the Earth. So what we're going to look at now is that earthquake occurring and being picked up by these seismometers. When you see the dot turn red, that means the ground below the station is moving up. When the dot turns blue, that means the ground below the station is moving down. There's the earthquake starting at that little star, and then you can see the different earthquake waves spreading out across the country. Now, it's important to see the scale down there, 22 nanometers. So this is less than the width of a human hair. These are incredibly sensitive instruments, but we can detect earthquakes of this size across the entire country. So, excuse me, these are different kinds of maps from that particular earthquake. The one on the right is showing the instrumentally measured shaking from that earthquake. The one on the left is showing the reported shaking from different people from that earthquake. So the areas in blue and green are weak to light shaking. Areas in yellow and orange are strong to very strong shaking. I live right over here in this area that had strong shaking, even though it was pretty far from the epicenter. And we're going to talk about why there was strong shaking there soon. But it was quite a irritation for me to move from the West Coast 10 years after this earthquake happened and have earthquake damage in my house. I was like, what? My house in Maryland. Anyway, there was quite a bit of damage, both near the epicenter and across the DC area. So the National Cathedral was damaged, lots of damages to chimneys, to unreinforced masonry buildings. Basically, those are like brick buildings. You all in Sparta, North Carolina had a lot of the same types of damage where you saw chimneys falling. Houses that had brick exteriors suffered quite a bit of damage in that area. And this is bringing me to the point talking about why we have different amounts of shaking in different areas. So every earthquake has one magnitude. Magnitude is the amount of energy that's released during the earthquake. But each earthquake can generate different amounts of shaking in different places. And that's usually dependent upon three things. The magnitude, of course, is important. Your distance from the earthquake is important. That makes sense, right? The closer you are to where the earthquake occurred, the more shaking you're likely to feel. But if we look at this map showing the instrumental shaking from, or the shaking recorded by seismometers during this earthquake in California, magnitude 7.1 Ridgecrest earthquake in 2019, we can see that there's some irregularities. It's not just a bullseye around where the earthquake happened. So the epicenter of the earthquake is marked by this star. It wasn't actually at the surface, right? This earthquake occurred far below the surface, about 10 miles below the surface. But there's also an area of red or very strong or violent shaking over here. And if you look, there's these areas of yellow that go up the valleys while the mountains are green and blue. So the valleys almost always shook harder than the mountains nearby. The local rock and soil conditions have a great deal to do with what you experience during an earthquake. So seismic waves travel through hard bedrock really well. They just plow right through it and off they go. But when they reach things like soft sand and soil, they have to slow down and get bigger in order to carry the same amount of energy. And so in the valleys in this soft sand and soil, you'll shake harder and for a longer period of time. It's almost like they act like jello. So here's an example. This is solid bedrock. This is an area of poorly consolidated sediment or soft sands and soils like a valley. And then this area over here would be water saturated sands and muds, like if you live near the beach or if you live near a river. So as the waves come through, they go right through the bedrock, then they slow down. And if you look at the seismograms, you can see the seismogram is bigger here from the same earthquake. And once they get into that water saturated sand and mud, then they're going to get even bigger. So the types of soil is really important. And after that Virginia earthquake, there were about 27 other seismometers that were deployed immediately afterwards. And y'all, let me tell you, some of my friends deployed those seismometers, and hats off to those people because it was August in Virginia, which means there were ticks, there were mosquitoes, there was poison ivy, and just a couple days after the earthquake, the hurricanes started coming through. So they were putting them out in a hurricane in August in Virginia. These are people dedicated to their science. Anyway, one of the things that they wanted to look at was how site amplification changed across the DC area. And so they put a seismometer on a DC bedrock site, and they put a seismometer in a site in DC that had some sediment. And this is what they found. So there was an earthquake, magnitude 3 in North Carolina. This was the seismic trace, or what was recorded by the seismometer on the bedrock site. And this is what was recorded from that earthquake on the sediment side, right? So much stronger amplitude of shaking, bigger earthquake waves. This was from a magnitude 6.8 in southern Alaska, and we see the same thing. There were much smaller waves on the DC bedrock site, and that basin amplification or that sediment amplification made those earthquake waves bigger in the sediments. And so this was the first study of its kind in Washington, D.C., and we expect to see the same sort of thing in places across the East Coast, including Baltimore, Maryland, Wilmington, Delaware, lots of different places. And this brings me to a really interesting thing that a lot of people haven't thought much about. I didn't, even though I studied earthquakes, until some of these earthquakes had happened. So I want to point out, these are all earthquakes of similar sizes, and each of these dots is showing people that reported feeling this earthquake. So here's the magnitude 6.0 Napa, California earthquake. And all of the dots that are in this orange color are people that reported feeling that earthquake. Now, if you look over here, this is a magnitude 4.1 earthquake that happened in Delaware. The purple dots are associated with people that felt that earthquake. The area over which these earthquakes were felt is very similar, even though the Napa, California earthquake was 700 times larger than the magnitude 4. Now, if we look at the 5.8 Pawnee, Oklahoma earthquake, that's the one in the mid-continent here. All of these red dots are associated with that earthquake. This was actually an induced earthquake or a man-made earthquake. And then over here, we have the Central Virginia earthquake that happened on August 23rd. And the green dots are associated with that earthquake. So this Central Virginia earthquake was actually felt by more people than any other earthquake in the history of the United States, partially because there's so many people in this part of the East Coast to feel it. But it was also felt from Canada all the way down to Florida and across to the Mississippi. Why? Why would you have earthquakes? I mean, this earthquake is like 5 times smaller than this Napa earthquake, and yet it was felt over such a massive distance. And we see this continuously. Earthquakes on the East Coast and in the Midwest are felt over areas about 10 times larger than similar magnitude earthquakes on the West Coast. And again, it has to do with the local rock and soil. So on the West Coast, you have a lot of active faults, newly active faults. They're having earthquakes all the time, and the crust over there is really hot. And so the seismic waves, it's almost like it's a big jumble, right? The seismic waves kind of get stuck on those faults. They don't transmit very well. Over here on the East Coast and the Midwest, we have really old rocks. Some of the rocks are 1 billion years old over here. We have the continental craton. It's dense, it's cold, it's old, and seismic waves travel through it so well, so they can be transmitted over much greater distances. We also have that nice blanket of sediment from the Appalachian Mountains that have been eroding for millions and millions of years. And so the waves travel really nicely through that as well. Also, a lot of these old fractures and cracks that we have on the East Coast, it's almost like they heal. So they haven't moved in a long time, and it's easier for the seismic waves to travel across them without getting stuck. So similar sized earthquakes on the East Coast to the West Coast, we're going to be felt over much greater distances. And this brings up a really important point. We often conflate the terms hazard and risk. So I want to take some time to talk about what that is. And I like this idea of a shark. So a hazard is something that has the potential to harm you, like a shark in the water. Risk is the likelihood of a hazard causing harm. So if you are standing on the beach and the shark is in the water, the hazard is there, but your risk is low. If you get into the water, now your risk has just gone up. People in California are used to earthquakes, right? They have built bridges that can withstand shaking. There's lots of seismic retrofitting. There are lots of building codes built to withstand seismic shaking. So even though there's a lot of earthquakes there, people are generally prepared for them. Now, if we think about the East Coast, what kind of hazards do we face? Well, we get hurricanes all the time. We have snowstorms, we have floods, and we tend to prepare for the hazards that occur the most often. I mean, that makes sense. If we only have X number of dollars, we put them towards the things that are the most likely. Excuse me. But what happens is that in California now, you have a high earthquake hazard, but you have a fairly low risk because people are prepared for that hazard. On the East Coast, we may have a low seismic hazard, but we have a high seismic risk. It's unlikely that the hazard will happen, but if it does, it has a fairly high likelihood of causing harm because our buildings aren't engineered to withstand earthquake shaking. our infrastructure, our roads and things aren't designed to withstand the motions of the ground. And in general, the people that live on the East Coast, man, we are prepared for hurricanes, right? Like we know what to do when there is a snowstorm. When there's an earthquake, everybody's like, uh-oh, what are we supposed to do? And I've heard hundreds and hundreds of stories about people on the East Coast that experienced the Virginia earthquake. And just about to a person, everybody was like, what is that? What am I supposed to do? Just because it's so infrequent. So all of those transplants from California are like, it's an earthquake. This is what you're supposed to do. I hear lots of stories about that, right? So let's go through some of the things that you can do to help decrease your earthquake risk. There is something called the Great Shakeout. It's a worldwide earthquake drill. And there are things that you can do for the central US, the Northeast, the Southeast, the upper Midwest. So there's regional advice that you can get. And then you can practice what you would do during an earthquake, because there is nowhere in the country that you can be that has zero earthquake risk. There's also a series of publications by the United States Geological Survey called Putting Down Roots in Earthquake Country. They have them regionally for all the different areas so that you can know what the things that you should do in your region are. You can also go to your state and local government, because they'll also, have resources on what you can do in the case of earthquakes or other hazards that don't happen as often, say, as hurricanes. But let's just briefly go through a couple of the things that you can do. Some of these are more applicable if you are in one of those seismic zones, for instance. So it's important, if you live in an area with a high seismic hazard, to, say, strap down your water heater. You also want to make sure that you secure bookcases to the wall. All of you that have little kids, we all know, right? You have those things that you strap your bookcases to the wall, you strap your dressers to the wall, because those little monkeys will climb up those things and we don't want to fall on it. Also good for earthquakes. You want to make sure to have an earthquake plan. This is good for any hazard. You want to make sure to have a hurricane plan, a tornado plan, a flood plan. Sit down with your family and your community and make sure that you know what to do, because these hazards can arise when you're at home or when you're separated from your family. Earthquakes can be really scary because we don't know when they're going to happen. So we have to plan for all those contingencies. You want to make sure to have an earthquake kit. Now, your earthquake kit can be the same thing as your hurricane kit. It's extra supplies, extra medications, batteries, radio, flashlight, extra medication. Don't forget about your pets, because they're part of your family too. So include food and water for pets in your emergency kit as well. If you live in a place like California, this is really, really relevant. You want to make sure that you have structural integrity of your building so it can withstand earthquake shaking. If it's a newer building, it may have been built to code, but if it's an older building, you want to make sure that it is bolted to the foundation and that you have shear support for the walls, because earthquakes don't just push the ground up and down. It's an upwards push, a sideways thrust, a downward drop, and a sideways thrust in the other direction. And that can be really difficult for some types of buildings to withstand. You want to make sure that you know what to do when you feel earthquake shaking. Say it with me. Drop, cover, and hold on. Do not stand in a doorway. That is an old, outdated thing to do. So you want to drop down to the ground, take cover underneath a sturdy object like a desk, and then hold on until all the shaking has stopped. After the earthquake has occurred, you want to make sure to clean up any hazardous materials. That may be broken glass. It could be chemical spills. You want to treat anyone that's injured. And then you want to go out into your community. You are far more likely to be rescued by one of your neighbors than you are by an emergency responder during an earthquake, just because the regional need is going to be great. And the ability for emergency responders to reach you in a really timely way is going to be small. So make sure you know the people in your community, especially make sure you know the vulnerable people in your community, people that may have mobility issues, the elderly, people that have small children. So check on each other. We have this feeling sometimes that after these types of events, there's going to be mayhem and riots. And we found that to not be the case. Communities come together. What we see more often are people that don't have electricity having huge neighborhood barbecues where they're sharing food and sharing resources. So it is an opportunity for the community to come together. I would argue that we should do that before the earthquake happens. So this is the 7 steps to earthquake safety, and this is available online freely from the Earthquake Country Alliance. And remember, Everywhere is earthquake country. And there's no reason to be scared of earthquakes. We just need to prepare for them. So, excuse me. Thank you for your attention. Here's my website. If you need me, you can find me across all social media platforms, except Twitch. Man, I have not figured out Twitch, and I'm far too old for Snapchat, but I'm on most of the other things. So just a brief thing about this sign. For my PhD, I worked in the Himalayas in the area of Indian-controlled Kashmir. So this is the sign on the border between India and Pakistan. And it is one of the single most random things I've ever seen. So without geography, you're nowhere. Random Jimmy Buffett quote at 16,000 feet. So thank you. If you have any questions, feel free to put them in the chat.
Wendy, thank you very much.
Sure.
Excellent stuff. Really, really interesting, very exciting stuff. I'm glad to know I don't have to be afraid of the rocks here in Raleigh, North Carolina, but I should probably keep tabs on them.
Yes. They're moving a little bit all of the time.
They're moving a little bit. Yeah, I'll invite everybody in the chat. Go ahead and drop your appreciations as well. Lots of clapping hands are showing up in the chat already for you. Excellent stuff. Okay, so I've been doing this job for a little while here with the museum. I've met some of the state's geologists and geologists who work adjacent to the state, and we've had a couple other geology presentations here. And so we've heard about the Sparta quake a little bit, and I've heard about fault lines and sort of the geologic history of North Carolina and the East Coast and the colliding and separating of continents. But some of the maps and the information that you were sharing here was kind of new to me, like the idea that most of these faults that are in our area are just deep underground, not waiting necessarily for anything to happen, but that all of these faults are places where things can happen. Particularly the map that showed all of the stresses, the 3 different types of stresses and how they're distributed across the country. Seeing that really kind of brought home this idea that you were getting at, which is, it's not like a ticking time bomb, but the stress is always there on the rock. There's always movement and motion that's happening, even in a place that's so quiet.
Mm-hmm. Yeah, earthquakes in the Midwest and on the East Coast happen. They happen more infrequently than on the West Coast. California, on average, has at least 14 earthquakes a day, just to give you an idea. And of those, however many hundreds of earthquakes they have every year, thousands of earthquakes they have every year, usually about 2 of them are large enough to cause damage. That's usually a 5.5 or greater. And on the whole East Coast, we have an earthquake of that size maybe once a decade. So while California, just that part of the West Coast, just to give you an idea of the frequency. And so it's a waiting game. We don't necessarily need to be holding our breath, but we need to be aware that it could happen and prepare for that. Because a lot of the preparation that we would do for earthquakes is the same preparation that we would do for other hazards.
I have to admit that in that Virginia quake in 2011, the August 23rd one, I was one of those people who just went, "What's that?"
Yeah. Well,
and then check Twitter.
I just got an alert from the USGS, which means there was a magnitude 7 or greater somewhere in the world. There was a magnitude 7.6 in Tonga. Earthquakes are happening all the time. And I feel like, it's one of those interesting phenomenon where when an earthquake sequence happens that's unusual, like the earthquake swarm in South Carolina, or like the earthquakes in Turkey, people become more aware of earthquakes just around the world. And they also become more a part of the news cycle. And so it seems like more earthquakes are happening. People start to go, "Oh my God, why are there so many earthquakes? This is terrifying." And so if you find yourself doing that, it can be helpful to sign up for some of these alerts. And then you're like, "Oh no, earthquakes are really happening everywhere all the time. It's just that very few of them are causing havoc."
So there's lots of questions coming in, and I'm going to get to the audience questions in just a moment. One that I had for you, when you showed us that for the Sparta quake, that there was the first documented rupture on the surface, at least here in the East, I think was the superlative there. Does the surface rupture make an earthquake more likely? Like if it's broken all the way through to the top, does that make more shaking more likely?
That's a really good question. So, you know how I said one of the components of what you feel during an earthquake is your distance away from the earthquake? That is, if you imagine looking at a map, that's like your driving distance, your distance away that way. But if we turn the map on its side and think about the earthquake is occurring here, it can also be your vertical distance away from the earthquake. So if the earthquake is close to the surface and ruptures all the way to the surface, that means that the people on the surface are very close to where the earthquake is happening. So often you'll experience more shaking with these shallow earthquakes than you will with earthquakes that are a little bit deeper.
Okay, I see. Are the earthquakes happening out west in California, the 14 a day, are they more shallow compared to earthquakes that are happening, say, here on the east, where I think you said the rock is older and...
Yeah, that's a good question. Most of the ones that occur on the East Coast that I'm aware of are also fairly shallow. Where we get really deep earthquakes are places where you have one plate subducting or diving down beneath another plate. So let me see, this earthquake in Tonga, which I don't know if y'all know where Tonga is. It's like the middle of the ocean, but this earthquake was 210 kilometers deep. And so earthquakes in California tend to be 6, 8, 10 kilometers. This one's 200 plus kilometers. They can be 500 kilometers. So it often depends on the type of fault as to how deep it is.
Okay, interesting stuff. Thank you. All right. So some questions for you from the chat. Let's see what these folks are thinking about. First one that comes up here, David wants to know, is South Carolina likely to receive most upcoming East Coast earthquakes?
No. There's those areas that we pointed out, the different seismic zones, those are the ones that tend to have a lot of earthquakes, those areas. And so that's parts of North Carolina, Virginia, Tennessee, also South Carolina. But South Carolina does, of all the states in the East Coast, it does have the highest seismic hazard. So that may not necessarily mean all of the earthquakes, but it does mean a higher likelihood of large earthquakes. My best friend lives in South Carolina, so I'm like with y'all on this. Like I talk to her about it all the time.
Yeah, I've got friends and family down in Charleston, and I feel like it is somewhat regular that I hear them talking about or hear about earthquakes that they're experiencing.
Yeah. And there's a lot of really great seismologists that live and work in the Charleston area. Steve Jummay is an excellent seismologist. He's at University of Charleston. He's fantastic. So if you're interested in, seismicity in your particular state, reaching out to some of the local geologists in the local geological survey, they can give you a whole lot of information that's very specific to those locations. We don't hear about it much. I feel bad for all our East Coast geologists, right? Because when you're on the West Coast and you're a geologist studying earthquakes, you're like talking all the time. But people on the East Coast, it's like slow and steady wins the race out here.
Right. But maybe, does that make it more interesting perhaps to be a geologist out here? Or is it just different?
It's just different. It's all interesting. I mean, we understand earthquakes that occur on the East Coast and in the Midwest are called interplate earthquakes. So they're happening on the interior of the plate. And we don't understand them very well. So there's a lot of active research that's happening. There's a lot of people working to understand what the subsurface looks like. Remember, I talked about that ultrasound wand almost. That helped to show a lot of the faults and structures that we didn't even know were there. So we're still looking at that data, trying to understand that data. So it's a huge area of active research, which is always interesting because you learn new stuff.
Next one for you. What is the risk of an earthquake in the coastal plain of Eastern North Carolina? Everybody's just like, okay, I need to know.
My place. I don't actually know specifically regionally what the different risks are. I would go to your state geological survey and look up earthquakes because they'll show the risk. The risk in the coastal plain usually in places like Virginia and North Carolina aren't from earthquakes occurring there. What you are likely to feel are seismic waves from earthquakes occurring in places closer to the mountains. For instance, the earthquake that did damage to my house in the Maryland coastal plain was in Mineral, Virginia, more than 100 kilometers away. So you're likely to feel shaking from earthquakes that are farther away. But shaking is shaking, whether it occurs right underneath of you or whether it occurs 100 kilometers away, it can still cause some fear and anxiety. And that's normal. It's okay to be a little bit scared. You just have to be prepared.
And similarly on that point, Michael was wondering when hiding out in door frames stopped being the advice.
So that
and
started.
You mentioned they were also experienced 1989 World Series earthquake in Candlestick Park, I think in San Francisco.
Yeah, Loma Prieta. Yeah, that actually started about 60 kilometers away, but most of the damage was in the San Francisco Bay Area because of the famous Bay mud that amplified the shaking so much that it basically destroyed the whole part of the city. But so there were all of these things in the West. And there's a famous image in one of the Red Cross pamphlets that shows an old adobe house, and everything has collapsed in that old adobe house except for the door frame. So if you live in an old adobe house, you can go to the door frame. But in today's modern construction, door frames are no longer the safest place to be. And in fact, one of the most common injuries during earthquakes are broken fingers from people trying hard to stand in the doorway and the door slamming on your fingers. So in the United States, in 2023, the biggest hazard that you have from earthquakes in most parts of the country is not the building collapsing on you. It's the things inside your house falling on you. Like this thing right here is a death trap. So I've got it, secured to the wall because if I can't get under my desk fast enough, this thing is going to squish me, right? The glass is going to break. All of the books are going to fall. And so thinking about the things that can fall on you, people will put like big pictures, artwork behind their bed. You're sleeping, an earthquake happens, and now this thing's on your head. So that's what we're trying to prevent against. That's why we want you to get under something, is so that things don't fall on you and injure you. Now, if you live in certain places that have some shaking and you're in an unreinforced masonry building, it has a big chimney, it has, brickwork, that can cause some damage depending on the way the chimney falls. Usually they peel outward and fall onto the ground, which is why you don't run outside during an earthquake. If you're outside, stay outside, move away from buildings, power lines, and trees. If you're inside, stay inside.
Good to know. All right, another one for you. Do you know what percentage of East Coast earthquakes might result from groundwater withdrawal or injection?
Yeah.
How these things are related to earthquakes?
Yes. Humans can cause earthquakes. It's called induced earthquakes. People often talk about fracking, which is basically hydraulic fracturing, where energy companies will take a slurry of water and some other materials and inject it into the ground in order to break up the rocks and extract things that are kind of stuck in the pore space of the rocks, whether that's oil or natural gas. Then they suck all that stuff back out again and take out what they want. The fracking itself can cause really small earthquakes, but that's not the problem. The problem is now the energy companies have this waste material that came out along with the hydrocarbon or whatever it is they were trying to get, and they want to get rid of it. And so the practice is called wastewater injection. And the idea is that you inject it really, really deep into the earth, which then acts as a sieve and cleans it out. The problem is when you inject water into the subsurface in places where that stress field are optimal, you can lubricate the faults, causing earthquakes to occur. There's not a lot of wastewater injection on the East Coast. There is some in Ohio. Pennsylvania, I think, sends all of their wastewater to Ohio. There's a lot of wastewater injection in Oklahoma and Kansas, northern Texas. In fact, in 2009, Oklahoma took the honor of having the most earthquakes in the US, even more than California and Alaska, because of wastewater injection, which is where that magnitude 5.8 Pawnee, Oklahoma earthquake occurred. So now that hydraulic fracturing, wastewater injection have been shown to induce earthquakes, there's a lot of regulation going on to make sure that the earthquakes that come from that, those earthquakes would have happened otherwise, but like over millions and millions and millions of years rather than 5 years. So there's more regulation that's happening to control those. And we don't have very much of a problem with that, at least in the southeast area.
Great stuff. All right, let's see here. We remember seeing a lot of media coverage from SCEMD on the swarm of small quakes around Elgin, South Carolina. Can you speak more on it? And is it possible in North Carolina?
Oh, yeah. So if you go to my webpage, I did a ton of interviews about the earthquakes in South Carolina because people were scared. And I get it. I mean, if you've lived there your whole life and suddenly you start feeling earthquakes, maybe one a month, that's disconcerting, right? I get it. And our human lives are very short blips on geologic timescales. So if you've lived somewhere for 50 years, geologically speaking, that's like a drop of sand in the bucket, right? So these things do happen. There was an earthquake swarm in Alabama. There could certainly be earthquake swarms in North Carolina. I can't recall any off the top of my head, but that doesn't mean that they're not possible and that they can't happen. So an earthquake swarm is basically just a different way that faults are behaving. What normally happens is you have an earthquake, a fairly large earthquake, say, no, it doesn't even have to be large. Let's say it's a magnitude 4. You have a magnitude 4 earthquake, and that will generate lots and lots of smaller earthquakes called aftershocks. And these are normal. That always happens after other earthquakes. A swarm is when you have lots of earthquakes of a similar magnitude, but there's no one big earthquake, no main shock that's then followed by aftershocks. You just have magnitude 2s and 3s happening all the time. And so it's just a different way that faults behave. There was I don't even know if it's still going on. There were 2 seismic swarms happening in Southern California last week, one in Nyland and one in Heber. And it was magnitude 3s and 4s. People were feeling them. They were like, what's going on? It's at the southern end of the San Andreas. Everybody's like, ooh, 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 bad news. And we're like, happens every year, all the time. So they happen. It's okay. It can be scary, but, again, don't be scared. Be prepared.
Have your plan.
Have your plan. Know what to do.
And then when everybody else is freaking out, you can appear very cool and collected.
Yeah.
You'll be that person in your community that's like, that's everybody. It's okay.
Mm-hmm.
I went to the Lunchtime Discovery series. I heard Dr. Wendy Bohon talk about this. We're going to be okay.
It's funny because most of the time when you feel earthquakes in places like North Carolina or South Carolina, the first thing most people think is that it's a truck going by outside. I felt an earthquake in the 5th grade in Virginia, and we thought that a car had hit the school because we were at a busy intersection. That's what most people think. It's quick, it's kind of a jolt, and it's the idea that it could be an earthquake is pretty far outside of our normal day-to-day experience. So we look for something, think of something like, oh, it was probably this other thing that's more likely, but sometimes it's an earthquake.
The folks with the Office of Environmental Education have been dropping links to a lot of great resources, like from the USGS and the North Carolina Geological Survey as well. So there's a lot of great things there. Folks, if you think you felt the shake, there's a bookmark the links, or just sort of keep these in mind, because you can get on the internet pretty quick and find out what's happened in and around you to maybe know what's going on. And as long as, take cover if you're in that kind of a situation, and then check the USGS and see what's going on.
And be sure to share your experience on the Did You Feel It page on the USGS site, because the information that you give us about what you experienced in your particular location tells us something about how the ground moves where you are. And because there's not as many seismometers on the East Coast as there are out West, that information is critical for us for making models to understand how the ground might shake in future earthquakes.
Excellent stuff. Wendy, thanks for being a part of the program again. This has been great.
Thanks so much for having me. It was really nice to talk to everybody. And I love all of your social media. So really quite an honor to be here. I appreciate it.
And everybody, thanks for tuning in for today's edition. We will be back here, of course, next Wednesday at noon. So I hope that I'll see you, I hope you'll see me again next week. I'll be here. I hope you will be too. Many thanks to the folks at the Office of Environmental Education and the digital media group here at the Museum of Natural Sciences. Everybody, take care. Plan your 7 steps. Be well, be kind. We'll see you again next time. Bye, everybody.